Hello and welcome to this next lecture on acoustics. Today I will touch upon some fine points. The first one is this, it is about the acoustic potential. So suppose we have the Euler equation which is given by del P dash is equal to minus rho 0 del U by del T. Then if I do a curl of this del cross del P dash, curl of a gradient being 0, I get minus rho 0. I will switch the operator in, del cross U, that is equal to 0, and if del cross U is 0, then its irrotational flow velocity is irrotational, then U can be written as a gradient of a scalar potential. Phi is a scalar potential. Now since U appears as a gradient of phi, phi actually could have been some phi star plus some g of t. Okay, it could have been some phi star plus g of t such that del of phi is del of phi star and this g of t goes to 0. Okay. Now so if any temporal quantity is added to this, the gradient of phi is not affected. Okay. Now let us see, getting back to the Euler equation, del of P dash is now minus rho 0 del by del t of the gradient of phi, okay, that is velocity, so that I have the gradient of P dash plus rho 0 del phi by del t is equal to 0. Okay. So that now if I integrate to remove the gradient, I get P dash is equal to minus rho 0 del phi by del t plus some other function of t only. Okay. Instead I am going to write this as minus rho 0 del by del t of phi plus gt, okay, or phi plus let us call it ft, phi plus ft, such that del f by del t is equal to g of t, or df by dt. It is a function of time only. So minus rho 0 df by dt is equal to gt. Okay. But now we have the linearized continuity which says del rho dash by del t plus rho 0 del dot u equal to 0, and P dash is equal to rho dash c square, the acoustic pressure per tube density, we know that. So I have 1 over c square del by del t P dash plus rho 0 del dot u equal to 0. Okay. U is now del phi. So that becomes plus rho 0 del square phi, that is equal to 0. Okay. Now what happens here? I have 1 over c squared del by del t, I will take it from here now, minus rho 0 del by del t phi plus f of t plus rho 0 del square phi equal to 0. Then rho 0 goes away. Okay. Let me bring it here so that I am on the same page. 1 over c square minus del 2 del t square phi minus 1 over c square del 2 del t square f of t plus del square phi equal to 0. Okay. So del square phi is there, 1 over c square del 2 phi del t square is there, acoustic wave equation is there, but I have this extra thing. Okay. So what we are saying is that there are several phi's which give you the same velocity, because gradient of phi is all that is needed. Okay. Once you take the gradient, the temporal term goes away. Okay. So amongst all of those, we are going to choose one where this component is 0. We are going to choose one of those where this component is 0. Once that is chosen, I have del square phi is equal to 1 over c square del 2 phi by del t square. It satisfies the wave equation. Okay. Then the velocity is a gradient of phi plus from here p dash is equal to minus rho 0 del t of phi. Okay. There is always a confusion with the temporal constant that comes from this integral. So that's how we have resolved it. We have chosen that particular phi, okay, where this one is 0, because why? Several of them satisfy this once gradient is brought in. Okay. So that is one point I wanted to make. The next point is we are looking at piston driven rigid ended duct. Okay. And that expression turned out to be p of xt is some constant in front, then cos of k L minus x by sin k L and some time. Okay. And the impedance turns out to be, the specific acoustic impedance turns out to be minus j rho 0 c cos k L by cot k L sin k L, rather cot k L. Okay. And you can see that at cos k L is 0. So the resonance condition is what? Resonance is cos k L is 0, or k L's are twice n minus 1 pi by 2 with n going from 1 to infinity. So you can also see that x equal to 0, you get a cos k L, and cos k L is 0. So at the piston you get a 0 pressure. This being rigid, you will get a maximum pressure. Okay. That is the resonance defined by this condition. Now at resonance both velocity and pressure will be high, although not at the same spatial point. Nodes of one are antinodes of the other, etc. But both will be high at this resonance. But at the driver the pressure is 0. The driver is presented with a 0 pressure. Okay. So this is the case we have seen, and it is an idealized situation. Okay. The point I want to make is, one is pressure at the driver is 0, the driver is presented with 0 pressure. Max pressure happens at the wall because it is rigid. Okay. What about velocity? Velocity is also high, okay, because they are related through the Euler equation. In harmonic sound fields, pressure velocity are related through Euler equation. So velocities will also be high, velocity be high somewhere, etc., etc., although it is 0 here. And if you go to higher order mode, similar antinodes and nodes will appear. Okay. But this is one part of the situation. You may be wondering, when pressure maxima should be the resonance, why do not we consider sin KL to be 0? Why do we go for the impedance and then set it, and then impedance is cos KL, and at sin KL you straight away get high pressures. Okay. The thing is that you have a duct over here and you are driving it with a piston with a certain velocity, but we never spoke of what is backing or supporting the piston. We just, okay, what is the piston made of? Okay. So now if I take sin KL to be 0 and the pressure goes to infinity, what will happen to the piston? Can it hold it? Can it hold its position? Pressure actually goes to infinity now. In the sin KL goes to 0, you get infinite pressure over here. So what happens to the piston? We have not answered that, or we did not include that. Okay. So I mean, if truly pressure starts to go to infinity, you have to do a coupled analysis. It is no more linear. First of all, you have to do a coupled analysis, and nothing goes to infinity. Okay. If you build it, actually nothing goes to infinity. But if you build it, how will you build it? You will build it, there is a duct, there is a piston, the piston has a mass, the piston is supported on a spring small s, the piston is backed by a damper, and of course there is a force acting, there is a force acting, harmonic force acting. Now in this case what happens? The impedance seen from the force, right, it is a common velocity junction, common velocity. So both impedances will add. So what you will get is the force is equal to Z mechanical total, let us say, velocity at 0 comma t is equal to Z md, which is the impedance of the spring mass damper system, okay, which is j m omega minus s over omega plus Z m0, which is the duct impedance, which is minus j O0 c capital S cot KL u of 0 comma t. Okay. This is discussed in Kinsler frame under pipes, okay, and within that combined systems. Okay. I should also mention that the first 2-week set of lectures till the acoustic wave equation, the material is largely from Kinsler and Frey. I have said it in the intro lecture, but I am saying it here, Kinsler and Frey. Anyway, so this issue has been discussed there. So now, to make it more realistic, if we put a little bit of a damping, amount of damping, okay, then the imaginary part of this impedance looks like m omega minus s over s should be small for the spring, s over omega, okay, minus the area rho 0 c s cos k l sin k l by sin square k l plus alpha L squared, where alpha is a damping constant, cos square k L, okay, that is equal to 0. Okay. So now if omega by k is equal to c, okay, then cos k L sin k L by sin square k L plus alpha L whole square cos square k L can be written as A times k L minus B over k L, where A is the ratio of the mass of the driver over fluid in the pipe, fluid mass in the pipe fluid mass, and B is the ratio of stiffnesses, stiffness of the driver, damping into L driver stiffness divided by SA into rho 0 c squared. This is the fluid stiffness. Okay. If the driver is light, that means A is small and B is smaller than 1, then the resonances are close to Kn L is equal to twice n minus 1 pi by 2. This is equal to the minus j rho 0 c cot k L. Okay. So the piston system is light and therefore 0 pressure occurs at the piston. Okay, velocity will be high and zero pressure occurs. That is what we have seen in class. Whereas that means the piston system is not accounted for. Whereas if driver is heavy, A and B are larger than 1, then you get resonances which are n pi. Okay. And that is when you will get a non-zero pressure at the surface of the piston. Okay. So in the expression pressure equal to some constant into cos k L minus x sin k L, the sin k L going to 0 is not realistic unless the piston side of the system is accounted for. Okay. So we have taken one part of the system in idealization, and that gives you this as the resonances. Okay. Now whether you get the full system and you analyze that means the piston plus the duct, okay, and you analyze them for one situation or the other, you will get high pressures and high velocities both. In harmonic sound fields. Okay, though not at the same spatial point. Okay, so this is telling only one part of the story. That's the idea. And if you want to talk of this being 0, you have to add the other part of the system. That's okay. I brought this up also because internal sound fields, when you have internal sound fields, in pressure you have, let us say, rectangular box, okay, rigid walled. Then we talk of a situation where the pressure everywhere is something in the front and denominator is kmnq squared minus k squared, and then k square matches kmnq square, you get infinite pressures. Okay, so this is also called a resonance. So I wanted to address that why here we call pressure being high as resonance, whereas in this case the pressure at the driver goes to 0, that we call the resonance. Okay, so that's not the issue. The issue is impedance is always seen from the driver face. Impedance implies from the surface of the driver, how the driver sees the system. Okay, so that in here only one side of the story is being addressed. Otherwise, in any resonance, whether you have a heavy driver system or a light driver system, in any resonance, including here where pressures are high, velocities also will be high. That part is okay through Euler equation. Okay, I suppose you see what I am trying to say here. The last subtle point I want to make is that there are many ways to solve acoustic systems mathematically. Okay, I will just give you a hint of another way or another system. Suppose I have a duct of a finite length. Okay. By the way, this I am presenting after chatting with Professor Chandrasekhar Jog of mechanical engineering at IISc. So now you could have an acceleration condition on the left and a pressure condition on the right, a transient acceleration and transient pressure condition. This is x equal to 0, this is x equal to h. Okay. Now if I have del 2 by del x square, p of x comma t is equal to 1 over c squared del 2 by del t squared, p of x comma t. If I take a Laplace transform on time, I get del 2 by del x square, p of x comma s minus s square by c square, p of x comma s equal to 0. Okay. Now I choose here, this is the one trick you can say as minus s square by a square. Then I get I will write this as del 2 by del x square. The same thing I'll write as p bar delta, okay, plus q square p bar delta is equal to 0. These are equivalent. This is equal to p bar delta. Okay, so that now p bar delta is function x comma s. So that my p bar delta is equal to c1 sin qx plus c2 cos qx. Okay, and at x equal to h I have what? P of t, which in the Laplace domain is p bar of s. Okay, so what I have is p bar of s is equal to c1 sin qh plus c2 cos qh. Okay, now we want to take care of this condition, acceleration. So what I have from here is del p bar delta by del x is equal to c1 q cos qx minus c2 q sin qx, and at x equal to 0 I have c1q. Okay, and from Euler equation this is minus rho times a of s. Okay, the Laplace transform of the acceleration, which means my c1 is equal to minus rho a bar of s by q. Okay, so in here c1 is figured out. I need c2. Okay, what would c2 be now? Using this, p bar of s is equal to minus rho a bar of s by q sine of qh plus c2 cos qh. Okay, from here c2 turns out to be p bar of s by cos of qh plus rho a bar of s sin qh by q cos qh. Okay, so if we combine c1 and c2, p bar delta is known. Okay, so what is p bar delta? X and s, that is equal to rho a bar of s sin qh minus x by q cos of qh plus p bar of s cos qx by cos qh. Okay, and then if we use the Euler equation, okay, we relate to del p by del x, okay, that is equal to minus rho, hold on, yeah, a bar of s cos q of h minus x into q by q cos qh plus P bar of S minus Q sine QX by cos QH. Okay, this is equal to minus rho A of S. From here the particle velocity is equal to A bar of S cos of Q H minus X by S cos of QH plus P bar Q sine of QX by cos of QH. Okay, this here is equal to minus rho S into U. Okay, so that results, so this is equal to minus rho S into U, which results in a division of this by S and minus rho, which gives me this, division of this by minus S and rho, so I get a rho and an S. Okay, the acceleration A bar is the derivative of the particle velocity, so that's what I have written over here. Okay, so the particle velocity is the left side divided by minus rho S. So minus rho S takes out the minus and rho gives an S, that's here. Minus is taken out, I get a rho S, that's this. Okay, so now we have cos of Q of H minus X by S into cos QH, let's say. Okay, this can be written as expansion in S, n going from 1 to infinity, Cn S plus lambda n A0 I plus Cn of 2 S minus lambda n A0 I. Okay, this is an expansion that can be done using the Heaviside formula. Okay, for expressing Laplace transforms in a series of poles, singularities. Okay, now here lambda n is equal to twice n minus 1 pi by 2h, n going from 1 to infinity, and the cos QH equal to 0 gives QH as 2n minus 1 pi by 2, n going from 1 to infinity. For example, the C0 can be found how? By multiplying with S, by multiplying with S, by multiplying with S, by multiplying with S, and taking the limit to 0. So we get C0 as limit cos Q H minus X by cos QH, that turns out to be equal to limit S tending to 0. Okay, that turns out to be 1. Okay, because Q contains S, if you recall. Q is equal to, or Q square is equal to minus S square by A0 square. Okay. So similarly you can find Cn1 and Cn2. Okay. For example, Cn1 is minus cos of lambda n of h minus x by sh sin lambda n h dq by ds. This is part of the Heaviside formula. Q is equal to lambda n, which turns out to be equal to minus 2 sin lambda n x by 2n minus 1 into pi, and Cn of 2 is equal to Cn of 1. Okay, I am just giving you that there is another possibility. Okay, now one thing is, if you had not taken q square is equal to minus s square by a0 square, if you had taken q square is equal to s square by a0 square, then you would have Cauchy hyperbolic type functions, and they would have roots on the imaginary axis. Okay, lambda n's are real over here, they are on the real axis. If we had taken q square is equal to s square over a0 square, you would have roots on the imaginary axis. But here, by specifically choosing q square is equal to minus s square over a0 square, you set it up so that now the results are on the real axis. Once they are on the real axis, you can use this Heaviside formula for partial fractions and then invert. Okay. Now once Cn1s and Cn2s are found, it's easy to invert because these are of minus lambda n a0 t I. Okay, e to the power a s, my at is 1 over s plus a, right? Laplace transform of e to the power minus at is 1 over s plus a. So you can invert them easily. Okay. So finally what happens? I'll just give you the final answer. This is not meant to be a real syllabus problem, but it's good to know. Then P delta is rho a0 summation n equal to 1 to infinity 4 cos lambda n x by twice n minus 1 pi integral 0 to t sin lambda n a0 tau a of t minus tau d tau minus twice a0 by h summation n equal to 1 to infinity minus 1 to the power n cos lambda n of x integral 0 to t sin lambda n a0 tau p of t minus tau d tau, and the particle velocity u is integral 0 to t a of tau d tau summation n equal to 1 to infinity for sin lambda n x by twice n minus 1 pi integral 0 to t cos lambda n a0 tau a of t minus tau d tau plus twice by rho h summation n 1 to infinity minus 1 to the power n sin lambda n x integral 0 to t cos lambda n a0 tau p of t minus tau d tau. Okay. This problem is just meant to give you what are the possibilities, okay, not strictly at the level of this course. I will close the lecture here. Thank you.